Topic 9 is about oxidation and reduction. Specifically, 9.1 is the introduction to oxidation reduction. These are going to be looking at reactions, and specifically within the reaction, we are identifying where electrons are going and where electrons are being taken from and who's accepting them, so on and so forth. Therefore, in order to do that and specifically zone in on the electrons, oxidation reduction reactions, also known as redox reactions, are usually explained in what are called half reactions. Half reactions are representations of what happens to one reactant out of the two in terms of its electron. All right, so we have magnesium, and we know magnesium reacts with oxygen. It burns a brilliant white, blinding white light, and you get a white ashy powder left behind on the magnesium strip. Here's the reaction. 2 magnesiums reacts with 1 oxygen to create 2 magnesium oxides. You're like, awesome, it's a reaction. But we cannot see where the electrons are at. And therefore, we need to go through and identify where are the electrons. And this is where half reactions come into play. I'm going to look at one reactant at a time and identify what is going on with that reactant. Looking at magnesium first. So we have our 2 magnesium. And we know magnesium, when put in an ionic compound like magnesium oxide, it creates a positive charge. A positive charge means you're losing electrons. Therefore, those 2 magnesiums turn into a two magnesium ions. And since we have 2 magnesiums, that means it has released 4 electrons. Oxygen. We know oxygen is going to become a negative based on its situation within an ionic compound. Therefore, it's going to take those 4 electrons. So we have oxygen plus 4 electrons to make 2 negative oxygens. Then from this, you can identify that we have made our ions. That means we have had from 2 elements, we have transferred electrons to make a compound. And that is what a redox reaction looks like. Now, magnesium's not only reacting with oxygen when it's burning, we also have nitrogen. We don't think of nitrogen reacting too often. It is a relatively inert gas, but it does react in very small amounts. So if we go through and we identify what is, or each half reaction, we can do the same thing. So again, we have our magnesium, and we just identified that magnesium releases 2 electrons for each one to create a +2 charge. And since we have 3 magnesiums there, that means we have 6 total electrons that are being released. Nitrogen is going to be the one who's accepting those electrons to create 2 nitrogen ions. And so here we have the ions that are formed due to the transfer of those electrons. This takes us to the terms of what is oxidation and reduction then. Oxidation, definition, is the loss of an electron or multiple electrons. In the previous example with magnesium and oxygen, or magnesium and nitrogen, magnesium was the element who was being oxidized because it was losing its electrons and becoming a positive ion. Reduction is therefore the opposite. It is the gain of an electron. Therefore, in the previous examples, the 2 elements that were gaining were either oxygen or nitrogen, and those were the ones gaining. Now we have our redox reaction. A redox reaction is when you identify one element and you're looking at, or one reactant, sorry, looking at one reactant, and where does the electron go? You cannot have just oxidation or just reduction. It is a redox reaction. Reduction, oxidation, reaction. There are some synonyms mnemonics in which you can use to remember what oxidation and reduction are. Leo goes Ger is one example. It's the one I like to do because I am a Leo. So lose electrons oxidized, gain electrons reduced. The other one is oil rig. Oxidation is loss and reduction is gain. Because technically, even though we're looking at the electrons, redox reactions are not solely electron movement. We could look at it in terms of hydrogen or proton movement, or in terms of oxygen or carbon. There's a lot of ways in which we can represent redox reactions. In chemistry, we tend to focus in on the electron. In physics, we focus in on the electron. In biology is where we look at the other elements that may partake. What we're going to be looking at first, and what's going to be used as a consistent trend throughout the rest of Topic 9, is this concept of an oxidation number. This is a value given to each atom. It measures that atom's electron control or possession it has relative to the atom in the pure element or in the compound that it has itself. So, if we're looking at the type of compounds that we are going to be working with, we have ionic compounds and covalent compounds as the majority of type of compounds. Ionic compounds are easy to identify the oxidation number. It's just based off the charge of the ion in the ionic compound. Covalent compounds are a little bit more tricky. What we have to do with covalent compounds, we have to exaggerate that unequal sharing of the electrons. Therefore, we're essentially saying there's a gain or loss of that electron to the more polar or the more electronegative element. And this allows us to track relative electron density in the compound, so on and so forth, going back to electron affinity and electronegativity. Some other bits of information you need to know when looking at oxidation numbers are the sign next to the number. If it is a positive sign, that means the atom has lost control over that electron or multiple electrons, very similar to a positive ion where it's lost electrons. If there's a negative sign, the atom has gained control over that or multiple electrons. The number in which we use is the number of electrons over which control has changed. So have you increased in a positive value, decreased in a positive value, so on and so forth, and we will do several examples of this. And something to keep in mind in the way in which we distinguish oxidation numbers versus charges. NIB, and I will do my best to do this as well. For a charge of an atom, you write the number first and then the plus or minus sign. So 2 plus, that will give us the charge. The oxidation number, the sign goes first and then your value, so plus 2. A lot of times, the charge of the atom is the oxidation number, so on and so forth, and that will be very typical for ionic compounds, but covalent compounds, we don't have necessarily identifiable charges. Therefore, we have to go through and determine them. And that is what the next set of rules is for. How do we determine these oxidation numbers? There are 6 steps in which we're going to work through. Step number 1. Elemental atoms oxidation number equals 0. Therefore, if we have just a pure element, like aluminum, its oxidation number is 0. Oxygen, oxidation number 0, so on and so forth, because they are in their pure state. Second step. In simple ions, like ionic compounds, the oxidation number is the charge of that ion. So here we have a variety of examples. So magnesium with a 2+ charge. That 2+ charge means it also has an oxidation number of +2. Oxygen with a 2- charge. Its oxidation number is -2. And nitrogen with a 3- charge gives us a -3. So you can go through and track ions and their oxidation number. Now that's not necessarily true when it's in a compound. This is just for simple ions. Step 3. The summation of all oxidation numbers in a neutral compound must equal 0. So if we have a compound like H2SO4, there's no overall charge on this compound. It is a neutral compound. Therefore, when we go and add up all the oxidation numbers, we need to have all those oxidation numbers equal 0. And that way, there's no overall charge. Something else, sorry, to add in part 3. If there is a charge on the compound, you need to take that charge into account of what the oxidation numbers will be. And we'll do some examples of those. Step 4. The summation of all oxidation numbers in polyatomic ions must equal the charge of that ion. And that goes for charged compounds as well. So if you have a compound like nitrate, it has a -1 charge, which means your oxidation number, when you add them up with nitrogen and oxygen, needs to equal a -1 charge. Again, we will do plenty of examples to practice this. Step 5. The usual oxidation numbers is usually the charge of the most common ion for that element. And we can predict that from the periodic table. That is not always the case though, as we'll see in step 6. But to give you some examples, if you look at the alkali metals like sodium and potassium, which are the most commonly used, their usual oxidation number, or what we call the oxidation state, is +1. That is their charge. There are no exceptions to this rule. Fluorine and most halogens are going to be -1. Oxygen is usually a -2, but it does have an exception with your peroxides. So when you have hydrogen peroxide, like H2O2, your oxygen is actually going to equal -1. Another example is when you have OF2, your oxygen is actually going to become a +2, and we'll explain why in a little bit in another example. Hydrogen is going to usually be +1. The only exception to that is what we call metal hydrides, when we're making an ionic compound with a hydrogen, like NaH, where we know Na has to have a +1 charge, therefore hydrogen is going to take on a -1 charge. And then chlorine will usually be -1 unless it's combined with an oxygen or a fluorine, in which case it's most likely going to take on a positive charge. Again, we will practice this. The last step, some elements' oxidation states or oxidation numbers will vary in different compounds. And so it's all based on what they're bound with and what kind of compound it's in. The most common elements that have varying oxidation states are nitrogen, phosphorus, sulfur, tin, lead, and all the transition metals. All right, so how do you actually run these steps then? Well, it's best to identify the easy oxidation numbers first, the ones that have a set number, and then go through and determine the others within the problem based on steps 3, 4. Yep. Okay. So here we have a variety of examples in which we're going to use. Starting with just elements. We have iron. So here we have pure iron. And from step 1, it says atoms in the elemental state have an oxidation number of 0. Step 2 says in simple ions, the oxidation number equals the charge of that ion. So we have a simple ion, iron, with a 2+ charge. Therefore, it has an oxidation number of +2. All right, here we have 2 simple compounds. No, going back, and you can look at step number 5 to go back and look at this information, but you can also probably figure it out based off its charges as well. We know oxygen, unless it's in a peroxide, carries a -2 charge. There's no overall charge here, so we need to make sure it equals 0. Therefore, we need, for our 2 hydrogens, each hydrogen is carrying a +1. So 2 times that +1 gives us a total of +2 charge. With that -2 charge, you have a neutral compound, just like writing an ionic compound. Here we have nitrogen trichloride. Chlorine has a -1 charge, unless it's with oxygen and fluorine. We have 3 of them. So this nitrogen, which is in a funky spot, we need to have a neutral compound, so we need to make sure it equals 0. So we have 3 -1 charges, which means nitrogen needs to carry a +3. And so here we have a covalent compound where you would think nitrogen would have a -3 charge based on what we understand from the periodic table. But because it's in a covalent compound, it doesn't necessarily have that situation. And therefore, it's carrying a +3, not charge, but a +3 oxidation state. And then just getting a little bit more complicated. Here we have H2SO4. Again, it is a neutral compound. So we need to make sure all this equals 0. Here we have hydrogen. So I'm going to write a +1. We do have 2 of them, so keep that in mind. Here we have oxygen, and it's not in a peroxide, so we have a -2 charge. And we do have 4 of them. We need to make sure this all equals 0. So what is sulfur then? So we have a grand total of 2 times 4 is, or -8. Here we have +2. So how do we get this to a 0? Well, that sulfur becomes a +6. Looking over at SO3 with a -2 charge, well, the overall charge needs to be -2 for our oxidation numbers. We know oxygen, there's 3 of them, and each of them brings a -2 or has a -2 oxidation number. So what is that sulfur then? Well, if we need to have an overall -2 oxidation state, and we have a -6 set with oxygen, that means that sulfur is going to be a +4. So here is an instance when you have 2 sulfurs, each with a different value, which is why this goes with number 6, where some elements' oxidation states vary in different compounds, depending on what it's with. One has hydrogen, the other does not. So my question to you is, which compound does sulfur have more control in? What is control? Well, you go back and you look at the negative and positive values. All right, so who has those controls? Well, the oxidation number represents that electron control. So the more negative value you have, the more control you have. The more positive value you have, the less control you have. So we had a sulfur with a negative or positive 6 oxidation number and a sulfur with a positive 4 oxidation number in the previous example. Which one has more control then? Which is more negative? The one that is more negative is the one with the lower positive value charge. So the sulfur in the SO3 2 negative compound or polyatomic ion is the one that has more control over the electrons. Once it becomes part of the sulfate compound, sulfur loses control over those electrons. Now we've been looking at just what's happening in the compound itself and identifying oxidation numbers, but what's going to occur within a reaction? So in a reaction, you're going to see potentially a changing in the value of the oxidation number. So if you change the oxidation number during a reaction, you have a redox reaction occurring. Not all reactions are redox reactions. You need to keep that in mind. And that's why you need to be able to identify what are the separate oxidation numbers in order to determine, is it a redox reaction? And further on in topic 9, we'll see what's the purpose of redox reactions and how we use them in industry. Starting with a simple reaction, how do we go through and identify if there's a change in oxidation numbers? So we have 2 hydrogen reacting with an oxygen to form 2 waters. We know elemental or elements, they have an oxidation number of 0. So both those start with 0. Then what's going on with water? Oxygen has an oxidation number of -2. Each hydrogen has an oxidation number of +1. So that hydrogen is going from a 0 to a +1. Oxygen is going from 0 to a -2. So who's being oxidized and who's being reduced? Let's go back and remember. What is oxidation? Oxidation is loss, or lose electrons oxidized. Who lost electrons? The hydrogen, because it made it more negative. Therefore, hydrogen is being oxidized. Reduction is gain, or gain electrons reduced. Oxygen became more negative, therefore it's being reduced. This is an oxidation-reduction reaction because there is a transfer of electrons and change in your oxidation state for elements or compounds. Looking at another example. Here we have calcium, pure element, so it's 0. Tin with a 2+ charge, so it's a simple ion, so it has an oxidation state of +2. Going over, calcium now is a simple ion, so it has a +2. And tin is now a neutral element, so it's 0. Again, what is going on here? So calcium went from 0 to +2. Tin went from +2 to 0. All right, so who's being oxidized? Lose electrons oxidized. Who's becoming more positive? We have calcium becoming more positive, so that is being oxidized. Gain electrons reduced. Who's becoming more negative? Tin, because it's getting closer to the 0 or negative side. So that is our reduction side. Again, you can't have one without the other. Looking at a little bit more complicated example now. We have to go through and identify what's going on in each of these elements. All right, so far what's happening with ammonia first. We know hydrogen has a +1. There's 3 of them, so that means our nitrogen needs to be a -3. Pure oxygen, 0. NO, O has a negative 2 charge, so this nitrogen has a positive 2 charge. Water, oxygen has a negative 2 charge, and hydrogen has a positive 1 oxidation number, and there's 2 of them. Let's list what's going on in each of these. So looking at nitrogen first, nitrogen's going from a negative 3 to a positive 2. Hydrogen is going from a plus 1 to a plus 1. And oxygen is going from 0 to negative 2. So nitrogen started from a negative 3, went to a positive 2. So that is losing electrons. That is oxidation. Nothing's happening with hydrogen. So it's not actually participating. It's like a spectator ion. Oxygen is going from 0 to negative 2. Therefore, it's gaining electrons and being reduced. This is a more complicated version of what's going on, but shows you not every element has to be oxidized or reduced, but it may need to be there to help transfer electrons or make compounds or allow the reaction to run. But this is still an oxidation reduction reaction because we have elements participating in oxidation and reduction. The last example all right, so going through each of these elements. What you can do, if you so choose, is you can, if you know that carbonate, CO3, as an ion carries a negative 2 charge, you can go through that process if you so choose. Or you can look at each individual element. I'll go through and look at each individual element. We know oxygen has a negative 2 charge. We know magnesium carries a positive 2 charge. There's a total of negative 6 on carbon, so that means oxygen needs to have, or carbon needs to have a positive 4. Iron is going to have a positive 2 because oxygen has a negative 2 and it's a 1-to-1 ratio. Looking at the product side, oxygen has negative 2, so this magnesium has to have a positive 2. We know oxygen has a negative 2, and that gives us a total of negative 6. Iron here is going to have a positive 2, and carbon's going to have a positive 4. If you wanted to look at it, like I had said with carbonate, looking at carbonate as an ion itself, since it's an ionic compound, carbonate carries a negative 2 charge. Therefore, it has an oxidation value of negative 2 overall when it's in an ionic compound, and that is why we also know that iron has a positive 2 charge. If you notice here, magnesium's positive 2, positive 2. Carbonate overall looking at carbon, positive 4, positive 4. Oxygens, all of them have negative 2, and iron has positive 2. So this reaction is not a redox reaction. And so I just wanted to be able to give you an example of not every reaction actually is a redox reaction. It is a reaction. There's transfer taking place, but there's no one element stronger than another to take electrons or transfer of electrons. So not every reaction has to be an oxidation reduction reaction. And the last bit of information is just going back to naming systems. So the Roman numerals for transition metals represent the oxidation state in which they have. Here's just some examples of what that means. So we have FeO. It's a 1-to-1 ratio. So we know oxygen has a negative or 2 negative charge. So iron has to have a 2 positive charge. Therefore, how we name it, iron 2 oxide, that is also its oxidation value. Here we have iron 3 chloride because this has a 2 negative charge, and that means this has to have a 3 negative charge in order to balance out, 3 positive. So iron 3 oxide, that is the oxidation state. manganese 4 oxide, which means that it's going to have a positive 4 oxidation number. And a manganate ion, like potassium permanganate, something along those lines. So it says manganate 7. So you know by that Roman numeral that that manganate is going to have a positive 7 charge. You could figure it out as well, because if you have oxygen, and we know oxygen's -2, there's 4 of them, so that's an overall -8. We need to make sure we have a -1 charge, which means we need to have +7 minus 8 gives you -1, so you could determine it in that method as well, just going back through the oxidation numbers as we have done previously.